Imagine a doctor diagnosing a patient using a checklist. Is the patient over 50? Does the patient have chest pain? Does their blood pressure exceed 140? That exact logic is how a decision tree works. At each node, it asks the most useful question it can, splits the data into two groups, and repeats on each group until every group is pure enough to call a prediction. Today, we're breaking down exactly how it learns those questions from data, and why it's the building block behind random forests and gradient-boosted trees. A tree has three kinds of components. The root node sits at the top. It holds the single most powerful question available across the entire dataset. Internal nodes are further questions on each branch, each one narrowing down the possibilities further. And leaf nodes are the final predictions. No more questions, just a class label or a numeric value. Every path from the root down to a leaf represents one complete decision rule. The depth of the tree is how many levels of questions it takes to reach any leaf. At each node, the algorithm tries every feature and every possible threshold, then picks the split that produces the cleanest separation. The standard measure of that cleanliness is Gini Impurity, 1 minus the sum of squared class probabilities. A Gini of 0 means a completely pure node where all samples belong to one class. A Gini of 0.5 means maximally mixed. Half of each class, no separation at all. Information gain is the reduction in Gini from parent to children. The algorithm picks whichever split maximizes that reduction. The tree is built greedily. Best local split at each node, which is fast but not guaranteed to produce the globally optimal tree. The problem is a fully grown tree memorises the training data. With enough depth, it can assign a unique leaf to every single training sample, achieving perfect training accuracy while being completely useless on new data. That is overfitting in its most extreme form. The fix is pruning. Set a maximum depth, a minimum number of samples required to split a node, or a minimum samples per leaf. These constraints force the tree to capture real patterns in the data instead of memorizing noise. A typical starting point is max depth of 3 to 5, enough to learn meaningful structure without going too deep. A random forest solves the same problem from the opposite direction. Instead of constraining one tree, it builds hundreds of them. Each tree trains on a random bootstrap sample of the data, and each split considers only a random subset of features rather than all of them. This makes every tree slightly different. The result is a diverse collection of trees that vote together. Classification takes the majority vote, regression takes the mean. Any single tree can be wrong, but the majority is far more reliable. The more trees you add, the more stable the predictions become. One major benefit of tree-based models is feature importance. Every time a feature is used in a split, you record how much it reduced Gini across the whole forest. Features used in many high-impact splits rise to the top. This tells you directly which variables your model actually relies on, and which ones you could safely remove entirely. Use a single decision tree when you need a model someone can audit, trace, and explain in plain language. Switch to random forest when accuracy matters more than interpretability. Either way, no feature scaling required, mixed data types work natively, and you get feature importance for free. Thanks for watching. If this helped, like, comment, and subscribe.